If I have a chemical reaction that's in a state of equilibrium, that equilibrium is a dynamic thing, which means it can shift towards the product side or it can shift towards the reactant side. And there are different things that we can do that can influence the position. We can influence whether it shifts to the products or to the reactants. And one of the first people to notice that and to describe the effects was a French chemist by the name of Henri Le Chatelier. And Le Chatelier stated that if an equilibrium system was disturbed, the system would always react to appear to oppose the change until a new equilibrium was reached. And then if it was disturbed again, it would react to oppose that change to establish new equilibrium, and over and over and over again. We will look at the effects of 3 different types of changes. So we can change the concentration of reactants or products. We can add something, or we can take something away. We could change the temperature of the system. We could heat the reaction vessel. We could cool the reaction vessel down. That will influence the equilibrium position. And we can also affect the volume or the pressure of the container. We can increase the pressure, which by decreasing the volume, or we can increase the volume, which will decrease the pressure. So we'll look at these one at a time. I'll start with concentration changes. So we have a reaction here, and in this reaction, we have carbon tetrachloride reacting with hydrofluoric acid to produce dichloro-difluoromethane and hydrochloric acid. And this reaction is in a state of equilibrium here. It can shift to the products, it can shift to the reactants. So you have to think a bit about the collision reaction theory. Let's say that this system establishes equilibrium with 50% products and 50% reactants. So it's half and half. Well, what that means is that in my container, if I have a reaction vessel, it means that I have all of these things floating around in here, right? I've got carbon tetrachlorides floating around. Well, they're liquid, but I've got hydrofluoric acid. I've got methane. I've got hydrochloric acid. And these things are colliding with each other. They're bouncing off the walls of their container. They're moving back and forth. And in order to have a forward reaction, these 2 reactants need to collide with each other. And every time they do, then if it's an effective collision, then they will react and form a set of products. But the reverse reaction is happening too. And in order for a reverse reaction to happen, that means that these 2 products need to collide with each other, and then they can form reactants again. So if you think about those processes, what would happen if you added a bunch of a reactant? So if I add a bunch of carbon tetrachloride to the reaction vessel, well, now there are going to be more effective collisions between this reactant and this reactant. Just by the nature of probability, there are more of those things floating around, so they're going to be more likely to run into each other. And so that's going to increase the rate of the forward reaction. So if I add a reactant to a system, it's going to produce an equilibrium shift forward to the right, because we're going to produce more product molecules that opposes the change. So in this example here, we can see my system. So here's the hydrofluoric acid. And as the reaction progressed, its concentration went down because it was reacting, and equilibrium was established here. Then this line here is the change, or the disturbance. And so what was the disturbance? Well, notice how the HF concentration spikes up along the line. These guys don't spike along the line, but they gradually increase. Then after the HF spikes, it decreases like this. So the change that's happened is the amount of HF has decreased, the amount of HCl has increased, the amount of the dichloro-difluoromethane has increased. So that's a shift towards the product side, right? Because my product concentrations went up after the disturbance, and the reactant concentration went down after the disturbance. This spike means what was the change that I made? Well, I added a bunch of HF right here because the concentration instantaneously went up. That's me dumping a bunch of HF into the system. If I remove something, then I'm going to cause less effective collisions to happen. Fewer effective collisions are going to happen. So let's say I remove a product. I remove a bunch of HCl. Now there's less of this product floating around. There are going to be less of these collisions between the two products. So the reverse reaction is going to slow down. The forward reaction doesn't slow down. It keeps going at the same rate. So this is going to cause a shift towards the right as well, towards the product side. If you remove a product, that will shift the equilibrium towards the right to produce more product molecules. So let's look at my system again. So equilibrium is initially established over here. And then here's the disturbance. I can see the HCl spikes down at the line. So that's a good hint that I removed that right here, after which the amount of HCl goes up, the amount of the dichloro-difluoromethane goes up, the amount of the HF goes down. And all those things are signs that the reaction equilibrium position is shifting towards the products, shifting to the right, to produce more products and less reactants. Now, what if I were to add a product? What if I added a whole mess of this product here? Can you think about the shift that that would cause? Well, that would cause more collisions between product molecules. That would cause a shift towards the reactants. Or what would happen if I removed a reactant? What if I removed HF from the system? Well, then I'd have fewer forward reaction collisions, right? I'd have fewer collisions between these reactants. And so then I would have less of the forward reaction, and that would cause a shift towards the reactants as well. So you notice that anytime I add something, it shifts away from that side. And anytime I remove something, it shifts towards that side to replace the thing that's been lost. And then I just have a couple of notes here. So you can recognize that the change we made was a concentration change because one reactant will spike up or down. It'll spike up if we added it. It will spike down if we removed it. And the second thing to note is that if we change the concentration, that has no effect on the equilibrium constant. So the Kc value stays the same. The new equilibrium position that's established would have the same Kc if we calculated it. Number 2, what about temperature changes? The first thing that you want to do when you get a reaction and you're being asked about a temperature change is you need to write the energy as a term in the equation. So if it's an endothermic reaction, put either the specific amount or just the word energy on the reactant side. And if it's exothermic, put the word energy or the specific amount on the product side. And if we're asking about energy, we have to tell you if it's endothermic or exothermic. We might do it by giving you an enthalpy value. You can go back to the enthalpy section to remind yourself about that. Or we might say it's endothermic or exothermic or give you some kind of a hint. Now, how will it work? Okay, if you're heating or cooling, remember you're adding or removing energy from the system. And once you've added the energy as a term in the equation, well, then you can treat it just like it's a reactant or like it's a product. So if heat is added, so if you heat up the system, the equilibrium will shift away from the side with the energy term. So if it's endothermic, like the top one, and we heat it up, that would cause a shift to the right, away from the energy term. If you remove heat, then the equilibrium will shift towards the side with the energy term because you're removing that thing. So if it's endothermic and you remove heat, that will cause a shift back towards the reactant side. Let's look at an example here. We have energy term here on the left. So this is an endothermic reaction. So if I heated this, that would cause a shift away from the energy term towards the product side. And if I cooled it, that would cause a shift towards the energy term towards the reactant side. So as long as you have the energy written out as a term in the equation, you can treat it just like it's a chemical entity. What if we give you a graph instead? So here's a reaction. We have a graph of the reaction here. I've got two reactants, my sulfur dioxide and my oxygen. Their concentrations start out high and they decrease with time. My sulfur trioxide increases over time. Here's my first equilibrium, and then here's my disturbance. Now, notice the first thing I want you to notice is that none of these things spike up or down along the line. That's a clue that this has to be an energy change. I must have heated or cooled this instead of adding something. Okay, so no spikes. That's my giveaway. Now, in order to figure out what thing happened, so was this a heating or a cooling, I have to translate this enthalpy into an energy term. So I have to write this as an energy term. So this enthalpy is negative, which of course means that this is an exothermic reaction. And so that means that the energy would be on the product side, right? So we're going to add the energy here, and now we can consider the energy as if it's a chemical entity. Now, we have to work backwards a little bit because we have to figure out which way it shifted, and then we can decide whether it was heated or cooled. So at the disturbance, my reactants concentrations went down. My product concentration goes up. So that means that it's shifting towards the product side. Now, this is an exothermic reaction. So what would cause it to shift towards the product side? If I remove heat. So if I cool the system, that would cause it to shift towards the product because it's exothermic. So the change that I made was I cooled it. Now, big star here, if you were writing a high stakes diploma exam, we would have you note that a temperature change is the one change here that does affect the equilibrium constant. Changes which make a reaction more products favored will have increased Kc values, right? Because Kc is a sign of being more products favored. And if the Kc decreases, that means we've made it more reactants favored. So we do cause a change to the Kc, the equilibrium constant. Now, why does this actually happen? Well, if we look at the reaction above, when I cool the system, it decreases both the forward and reverse reaction rates because the particles are moving slower. They collide with each other less often. But the reverse rate decreases more than the forward rate. So overall, it still is going to shift towards the products. And that's going to release more heat energy. Finally, pressure or volume changes. And these are really the same thing because you affect the volume by changing the pressure, or you affect the pressure by changing the volume, right? Or vice versa. So remember that pressure and volume are inversely proportional. Pressure of a closed system increases, the volume decreases, and vice versa. What you need to think about here is the fact that gaseous entities take up a lot of space. So if you have a bunch of gases floating around in a container, let's represent these guys. I've got sulfur dioxides and oxygens. So let's do these guys as some different dots. So my sulfur dioxides we'll do as a pink dot, and my oxygen we'll do as a blue dot. And then here are my products, these sulfur trioxides. And we'll do those as a green dot. Now, these things are all floating around, right? They're all gases, so they're bumping into each other. They're bumping off the walls into the walls of the container, etc. You'll notice that there are 3 moles of reactants and 2 moles of products. We've got more reactant molecules than we have product molecules. So if I compress this system, I decrease the volume, I make it smaller, I take the space away, that's going to cause more collisions between these reactants, which is going to turn them into products. Because there are fewer molecules of products, it's going to be happier. The system's going to be happier existing as more molecules of products. But if I make, so it's good, that's going to cause it to shift towards the product side. But if I make my reaction vessel bigger, then there are going to be fewer collisions overall, and that's going to favor the side that has more gaseous entities. So that would cause a shift back towards the reactant side because there's lots of room for these guys to spread out. They don't collide with each other as often. So to summarize, if I increase the volume, which means I decrease the pressure, that will cause a shift towards the side with a larger number of moles of gaseous entities. We don't care about solids or liquids or aqueous things. We only care about gases because they are the ones that are floating around, colliding with each other. If there's a decrease in volume, which we can accomplish by increasing pressure or vice versa, this will cause a shift towards the side with a smaller number of moles of gaseous entities because of the collisions. Now let's take a look at an example. So this is an example from this reaction up here. We establish equilibrium, and then here's my disturbance at the line. Now, notice the spikes. This guy spikes, this guy spikes, this guy spikes. All three things spike up along the line. And they're all gases. That's a sign either that I added a bunch of all three of those things at once, which we're not going to do, or I change the size of the container. Because if I change the size of the container, then I change the volume of the container, I instantaneously change the concentration value, right? Without changing the number of moles. And if I change the volume for all three of these by making the container bigger or smaller, then I'm going to instantaneously change the concentration. So all three things spiking along the line, that's my smoking gun, that this has got to be a volume or pressure change. Now, what was the change? Okay, well, let's look at the shifts. So my reactants here, after the disturbance, their concentrations go down. My product concentration goes up after the disturbance. So that means that this system is shifting towards the product side. The amount of product goes up. Now, what change would cause that? Well, I've got only 2 moles of gaseous entities over here. I've got 3 moles of gaseous entities on the reactant side. So it will shift to the product side if I make the container smaller. So that means that I increased the pressure by decreasing the volume. I made the container smaller in this case. That was the disturbance that happened along the line. And a second clue that that's what happened is all of these concentrations instantaneously go up. I can instantaneously make the concentration of a gas go up if I make the volume smaller. Now let's note a couple of things. A system with equal amounts of gas on each side isn't going to be affected by changes in volume. You can make it bigger or smaller all day long. It will not affect it. Same is true for systems with only solids or liquids. Note, if you add or remove gases that are not involved in the reaction, like inert gases. So say up here, we increase the pressure by pumping a bunch of argon into this reaction vessel. That will change the pressure, but it won't affect the equilibrium. Why not? Because it doesn't cause any more effective collisions to happen between reactant or product entities. The collisions are happening now with the inert gas, which is inert, means it's non-reactive. You can recognize this because everybody spikes, and we do not change the Kc when we make volume/pressure changes.